Welcome, wherever you are. Mr. David here. I want to take you through Chemistry Practical Paper 3, July-August mocks. Practical Paper 3 first, you need to be very careful. You need to read the procedure carefully. The procedure is the one which gives the instructions on what to do, so do not ignore the instructions. So let's start. You are provided with solid K. So you can say solid K is a magnesium ribbon. Then you are provided with solution L. Solution L is 2 molar hydrochloric acid. So 2 molar. Molar means what? Molarity. Capital M stands for molarity, and the molarity is the number of moles in a liter. So this simply means that the 2.0 capital M, this is the number of moles which are contained in a liter, and a liter is equal to 1000 centimeters cube. A liter is equal to 1000 centimeters cube. This solution C, sodium hydroxide, it implies here that 0.4 capital M, this is the number of moles which are contained in 1 liter, and the 1 liter is equal to 1000 centimeters cube. That's what it means. You are required to, so you have been given the stopwatch. You are required to determine the rate of reaction between magnesium and HCl at the different concentrations, then magnesium, the mass of magnesium ribbon. So let's go through the procedure. Place the 5 test tubes on test tube rack and label them 1, 2, 3, 4, 5. Using a 10 centimeters cube measuring cylinder, measure out the volumes of 2 molar hydrochloric acid. Solution L as shown in the table below. So we will see the table. So we will label the test tube number 1 to number 6. Retain the remaining solution. Following instructions is important. Do not pour. When you are told to retain, make sure you retain the remaining solution because you will need it. Retain the remaining solution L for use in question 2 and 3. Wash the measuring cylinder and use it to measure volumes of water as indicated in the table, and pour it into the corresponding test tubes. Cut out 6 pieces of each exactly 1 centimeter length and of the magnesium ribbon solid K. Then now Roman 3 is the most important, what you are supposed to do. Transfer all the solution in test tube 1. Now you have measured all the solutions into test tubes. You have 10 centimeters cube of solution L, 10 centimeters, 9 centimeters, up to 5 centimeters in test tube 6. So now you are required, in the first one you will add you will add 0 water. So let's look at the instructions. Transfer all the solution in test tube 1 into a clean 100 centimeters beaker. Place 1 piece of magnesium ribbon into the beaker and start the stopwatch immediately. Swirl, to swirl ni kusungusha the beaker continuously, ensuring the magnesium is always inside the solution. Record in table 1 the time taken for the magnesium ribbon to disappear. Carefully transfer the content of the beaker. After the reaction has ended, you need to transfer the content into the 250 ml volumetric flask. Add 10 centimeters cube of distilled water into the beaker. Swirl and add it into the volumetric flask. This is to ensure that all the content in the beaker is put into this one. Now we are done with that. Once you have done the first procedure, you repeat the procedure 3 for each of the solution 2, 3 up to 6. Then complete the table below. Now this is our table. Here, remember now it is concentration. We are looking at the rate of reaction in different concentration. When this is HCl, remember this is HCl, 10 centimeters no water added. 9 centimeters, 1 centimeters cube. So as you move to the right, the dilution, the solution becomes more diluted. It means that the time taken for the magnesium to disappear here will be very high. The time will be very high, and here time will be very small, less. It will take a few seconds to disappear. Because now that is the as you write the values inside here, we expect the trend. That is what we call the trend. The trend is that time in seconds must increase as you move this way. Time must increase. That is the trend. Then you have been given the rate. Rate is 1 over t. Why do we multiply with 1,000? Because you will get this one as 0.00 something here. Now you need to multiply to 1,000 to make it a number like 45, so that you can now draw the graph carefully, correctly. This is our table. You can see when time is, in test tube 1, when the concentration is 10, when the concentration has not been diluted, it takes 22 seconds. Then 9, that is 10 when water 1 centimeter is added. Time, you can see time is increasing as you go up to 90 seconds. So you can see the rate of reaction decreases as concentration, the time or the rate of reaction decreases as concentration decreases, and also time increases where the concentration is high. Did you hear that? Yes, you can see now the rate here is 45. Here is 35, 26, 22, like that. When we multiply with 1,000, that is it. Now that is the trend. For you to get all these marks, you need to be aware of this. Now plot the graph rate vertical axis against the volume solution. So on the vertical, you write a rate of reaction. Then you write this information here, 1 times per second. Then here you will be required to write the volume of solution L. Volume of solution L. You write solution in full. Now then you will be able to draw the graph. Now this is the graph. Now I want to remind you something. The graph of rate against something, rate against, is always a straight line which passes through the origin, which passes through 0, 0. Now look at this one. When the volume was 2, let's use our table, when the volume is 10, the rate is 45. When the volume is 10, the rate, you can see, is 45. That is what we are put here. When the rate is that, now we have these points here, or we have all of the points. We have this point, we have this point here, we have this point, we have this point, we have this point, this one, and I think there was another one. Yeah, there's this one here, and there is this one. One thing which you must have in mind is that any graph for the rate of reaction against, if it is rate 1 over t against whatever it is, sort of volume or volume of a solution or whatever it is, then the graph must come through the origin here, O. So what you need to do is to take the points which will lead you to the origin. Take the points which will lead you to the origin. That's how we choose a line. We draw a line of paste fit from the origin, taking the points, these points here. So it takes this point and these points. The others will remain out. The key word is the graph must pass through the origin, without which everything is 0. Using the graph, determine the rate that using the graph, determine the time that it would be taken for 1 centimeters length of magnesium ribbon to disappear if the volume of this acid is 7.5. So you come here to the graph where we have 7.5. This is a 6, this is 7, then 7.5 is here. So you draw a dotted line because you have been from the graph. Using the graph, you need to show this line here. So you draw a dotted graph, then you come, you find this one is around 24. So it will take, the rate will be 24. The rate will be 24. So time 1 over t times 1000 is equal to 24.5. So that is 1 over t. So if you want to get time, because what we want is time in seconds, you can remove this one here. We will have 1000 is equal to 24.5 t. We want time. You divide by 24.5, you divide by 24.5, you will get that the time is 40.8 seconds. When the volume will be 7.5, the time will be 40 seconds, 48.8.2. Procedure 2. To the content from procedure 1, now the content you poured into the volumetric flask, add distilled water while shaking up to the mark. Label this solution solution D. Remember what we have, solution D is HCl. But the difference between HCl D, solution D, and solution L is the concentration. This one has been diluted. That is the difference, right? Yes. Add distilled water. Fill the puree with solution C. Solution C, it is sodium hydroxide. If you doubt, you go back and check what you had as solution C. Solution C is sodium hydroxide. So sodium hydroxide is going to react with solution D, which is hydrochloric acid, which reacted with magnesium. So we are going to use now the excess number of moles that remained, the excess. Fill the puree with solution C. Pipette 25 centimeters cube of solution D into the volumetric 250 centimeters conical flask. Add 3 drops of phenolphthalein indicator, titrate against C. So here the key word, you need to understand that it is sodium hydroxide reacting with HCl. Very important. That's the only thing you need to. So what we have in the conical flask, whatever is inside the conical flask is solution D. Solution D is our HCl. Whatever we have in the purate, what we have in the purate is solution C. Solution C is sodium hydroxide. That understanding alone is very important. So you will not confuse anything when you have that understanding. So the total volume for each titration is 4 here, 24 point. Here I have 20. Okay, let me write here 20.4, 20.5, 20 point. Suppose you get here minus 23, and I want to teach something here. Suppose you get that yours here is 20.9. Now if you get 20.9 here, you will use it 0.9. Initial always 0.0, just use 0.0. 1 decimal place, use 1 decimal place always. We will have this one. Now, but when you are going to do the average, you will not include this one. You will leave out this one. Now you will do the average with 20.4 plus 20.5 divided by 2. That is when 1 is out of, it is an outlier. You can see the difference between 2.4 and 20.4 and 20.9, that is 0.5. That is a lot. We need you do average the one which is plus or minus 0.2, plus or minus 0.2. So you cannot do the average with this one. That gives you a wrong mark. It means you don't know what you are doing. Therefore mine was 2.3. If it is 20.3, then I will do, you can see the difference between here and here is 0.1. The difference between here and here is 0.2. Here and here 0.1. Therefore I can do the average with all of them. So the average, you will do 20.4 plus 20.5 plus 20.3. You divide it by 3 and you write the answer direct as 20. You press the calculator and you write. They usually say that you write the answer in 2 centimeters, 2 decimal places. You can add 0 centimeters cube to make it 2 decimal places. Calculated the number of moles of sodium hydroxide solution C. Now solution C, remember we were given the concentration of solution C. We were told C is 0.4 capital M. That one you must go back to what you are provided and check. So you are provided with 0.4 molar. That means now we can get the number, but now you need to know how much did you use in this reaction, in this experiment C. C, we have used 20.4 centimeters cube. Therefore, now we can get the number of moles of the sodium hydroxide used. We used 20.4 because C, this is solution C. Sodium hydroxide is C, and the average is 20.4. That understanding is good because you will not make any mistake. So now you are being asked the number of moles in the solution we used, C that we used. But we know that we were given that 0.4 is the number of moles which is found in 1000 centimeters cube. So we will ask the one we used is 0.20 this one centimeters cube. Which number of moles will it contain? So here we will come here and say 20.4 times 0.4. You divide by 1000 and you get the number of moles as 0.00816. That is the number of moles that is contained in 20.4 centimeters cube of sodium hydroxide we used. For those who want to use a formula, there is a formula, there is a table. For those who, if you have, there is this table here. Moles, molarity, then volume in liters. Volume in liters. So I want number of moles because the question is asking number of moles. I have the molarity of the solution and I have the volume. So to get the number of moles, so moles is equal to molarity times volume in liters. That volume must be in liters. So our molarity is 0.4 times the volume we used is 20.4. This is in centimeters. Let's convert it to liters. You divide it by 1000 and that tells you, gives you back there, which is 0.00816. Correct? Determine the number of moles of hydrochloric acid is 25 centimeters solution D. Solution D has reacted with solution C, and the mole ratio, when you write the equation here, sodium hydroxide plus HCl, this is a neutralization reaction which gives you sodium chloride plus water. If that is the case, then you can see the ratio, the mole ratio is 1 to 1. So the ratio, mole ratio is 1 to 1. It means the number of moles of sodium hydroxide is exactly equal to the number of moles of HCl. Therefore, moles of 25 centimeters cube D is exactly equal to this 0.00816 because the ratio is 1 to 1. Hydrochloric acid, number of moles of hydrochloric acid in 2/5 of solution D. Number of moles in 2/5 of solution D. That is correct. Now if we know the number of moles in 25 in 250 will not be, so we know that 0.00816 is the number of moles of solution D which are contained in 205 centimeters cube. Because D we used 25, we pipetted 25, right? Yeah, so some people will wonder hydrochloric acid 25 inatoka wapi? Unarudi kwa procedure. You were told fill the purity with solution D, then pipette pipette 25 of solution D. Pipette hilo unavuruta na kwa mdomo ama unatumia the whatever. So it is 25 centimeters cube. When you the pipette carries exactly 25 centimeters cube, not more than that. Now we know that this one is in D is into, so what about 250 centimeters cube of D will contain what? So it is 250 times this divided by that, and you will get the answer is 0.0816 moles. So this is the number of moles in 250. So now the volume that we had in 250 contains this number of moles. Then get the number of hydrochloric acid 50 centimeters of solution L. The solution L, we were given that 2 molar, that is 2 moles, are contained in 1000. So we will ask 50 centimeters cube will contain how many? That is 50 times 2, you divide by 1000, and you will get as 0.01 0.1 moles. So that is the number of moles in. Now this is the number of moles that was there initially in the 50, which was picked and reacted with the magnesium. Magnesium reacted with 50 centimeters cube. Now the 50 centimeters cube, which after the reaction, the same volume was added into the volumetric flask to give us this number of moles. Now we want to see the number of moles of HCl that reacted with magnesium. If we have this one as the number of moles that remained in 250 centimeters cube, the volumetric flask solution, we subtract this one to get the number of moles that reacted with magnesium. So it is 0.1, you subtract 0.0816 to give you 0.0184 moles. This is the number of moles of HCl that reacted with magnesium ribbon. Determine the mass of magnesium. Given that the RAM of magnesium is 24, then mass is equal to moles times RAM, 0.0184 times 24, 0.0 0.4416 grams. You are provided with solid E. Carry out the following test and write your observations and inferences in the spaces provided. Place all solid E in the boiling tube. Add about 10 centimeters of centimeters cube of distilled water and shake thoroughly. Filter the mixture into another boiling tube. Retain the filtrate for use in the 2 Roman B below. Dry the residue using the pieces of filter paper. So we will have the filtrate and the residue. Both of them are going to be used, so make sure you follow the instructions. Retain. When you are told to retain, it means keep it safe. Place the residue in a dry test tube. Add 4 centimeters cube of 2 molar hydrochloric acid solution. Retain in the mixture. Retain the mixture for test 3 Roman 3 below. Now you need to place the residue in the test tube. Add for whenever you are adding an acid to either a solution to a dry residue, you expect effervescence. Effervescence is the first thing you need to remember to expect. You must expect effervescence. And again, we want to see whether when you add these two molar hydrochloric acid to the residue, does it dissolve to form a colorless solution, or does it dissolve to form a colored solution, either blue, brown, green, or which one? So for this one, you write that it dissolves to form a colorless solution. Then it produces effervescence. Producing effervescence. Effervescence means bubbles of a colorless gas or is produced. A colorless. So for this one, first you need to separate them like this. You write in the inference. You write that the residue dissolve to form a colorless solution. So if it first the precipitate, the residue as dissolved in the acid to form a colorless solution, it means that the colored ions are absent. It means that copper 2 ions, the ion 2 and ion 3 are absent. These ones are absent. You write absent. Do not forget, don't just write this one and leave it. You must write that absent. Then we expect effervescence. Then did the effervescence occur or it did not? So effervescence, you need to tell us, did it bubbles? Did you see some bubbles? Yes or no? So bubbles of a colorless gas are produced. So bubbles of a colorless gas, this simply means effervescence occurs. You can simply write effervescence occurs. So if you don't write bubbles of a colorless gas are produced, just write effervescence occurs. So if effervescence, what causes effervescence? What causes effervescence is that there is a carbonate, there could be a sulfite, and also even a hydrogen carbonate. There could be an hydrogen carbonate. There could be an hydrogen carbonate. There could be an hydrogen carbonate. This is, yeah. So these three gives effervescence. This one, if it is a sulfite, there is a carbonate, there is this one, it will give effervescence. Then don't forget, so it means these ones are present. The word present and absent is very important, like I have told you. To the second, to 2 centimeters of a solution obtained in it. So the solution now, this colorless solution you have here, add aqueous ammonia dropwise until in excess. Dropwise until in excess. So you need to know what the observations the inferences you expect, or the observations you expect when you are using ammonia. We have 3 major ones. It is either the white precipitate is formed which dissolves in excess, or a white precipitate is formed which does not dissolve, or there is no white precipitate. Those are the 3 observations we expect. So in this case, the white precipitate dissolved and the white precipitate was formed which was soluble in excess. If that is the case and we are using ammonia, then always be aware that it is zinc 2 ions are present. Zinc 2 ions are present. Use about 2 centimeters of the filtrate. Now we are using the filtrate. What we used here is the solutions formed from the residue. Having that understanding is okay, is good. this, what we have here is the solution from the residue, but now we are going back to the filtrate that you filtered. Use 2 centimeters of the filtrate obtained in above. Add ammonia. Now you are adding ammonia. A white precipitate is formed which does not dissolve in excess, insoluble in excess. We are using ammonia. So if it is in it means zinc is absent. If it is the insoluble in excess, zinc is absent. Then what is present? Magnesium 2 ions are present, aluminium ion 3, red 2 ions could be present. So here the instructions, if when you give the 3 ions, you get 1 mark. When you give 2, you get 1 have a mark. When you give 1, you get 0 mark. Add about 2 centimeters of 2 molar hydrochloric acid solution L into the filtrate. So what is the observation? The observation is that there was no bubbles, there was no effervescence, there was no fizzing. So either do not write all of them, just write no bubbles or no effervescence or no fizzing sound. Then we expect a precipitate, because we are adding this one. Is there a white precipitate? Because hydrochloric acid, so no effervescence, it means the sulfite and the carbonate are absent. No white precipitate. HCl is expected to form a white precipitate with lead. So if the lead is absent, then what is present is magnesium and aluminium. Where did we get this one? You go back here. We said magnesium is present, aluminium is present, and lead is present. If lead was present, it would form a white precipitate. Now that there is no white precipitate, then it means magnesium and aluminium are the one present, lead is absent. Add sodium hydroxide to a dropwise until in excess. A white precipitate is formed, insoluble in excess. Then it means magnesium ions are present, aluminium is absent. Add 3 drops of barium nitrate. Barium nitrate will form a white precipitate. Barium nitrate will form a white precipitate with the sulfate, with the sulfite, and the carbonate. So remember, from here we have said that the sulfite and the carbonate are absent because we are using the filtrate solution. So if they are absent, there is no way you come here, a white pipette is formed, then you write the 3. Once you write the 3, you will penalize 44 and contra. That will be a contradiction ion, and you will get nothing. So these ones we have already said up there that they were absent. So if you come down here and say they are present, that is a contradiction, you get 0. So here you only write the sulfate ions present. You are provided with solid F. Carry out the following test. Write your observations and inferences in the space provided. I want you to mark here the root of the question, solid F. You are provided with solid F. When they say you are provided with organic solid F, there is a difference between this and there is a difference between this. Now as we move on, you will see the difference. Place solid or solid F in the boiling tube, add distilled water, then label the solution F. Add about a half of the sodium hydrogen carbonate provided into the solution. Now when we are adding sodium hydrogen carbonate or sodium carbonate, we expect effervescence when we are dealing with organic analysis. Now here there is no effervescence. You write either no bubbles, no effervescence, or no fizzing. Use one word out of that. You see the correct answer here is this one or this one, absent. I encourage you to use hydrogen ions absent. It is absent. If there was effervescence, you write hydrogen ions present. any student who will write here R COOH, which is represents this is the function for the organic acids, alkanoic acids. This is the functional group for alkanoic acids. Any students who will write this one absent will be ignored. They will write ignore this one. Why did they write ignore? It is because they did not tell you that it was an organic compound. If they said organic solid, then this is the correct one. And if they said organic solid, then you write hydrogen ions absent, you get 0. So you need to take care of the root of the question. If they say organic solid F, then the correct word, the correct here, you write R-COOH absent. Like now they have not included the word organic, do not use this one. You write this one. Add about 10 centimeters of dilute hydrochloric acid, solution L, to the rest of the solid solution F in the boiling tube. Filter and mix the mixture. Wash the residue with about 2 centimeters of distilled water. Dry the residue between filter papers. Place about 1/3 of the dry residue on a metallic spatula and burn it in the Bunsen burner. So I have told you practical is following these instructions. So it burns with sooty yellow flame or smoky yellow flame, whichever you use is okay. So if it burns with a yellow, remember that is it means whatever is burning is unsaturated, and unsaturated we have alkenes and alkynes. Those are the two correct answers. So you write this functional group correctly. You must ensure that the double bond we have each carbon should be surrounded with 4 covalent bonds, or you write negative, not negative, sorry, this one present, this one is a present, or you can simply write long chained organic compound present. That one is acceptable. So you write this or this present. Ensure that each carbon is surrounded with 4 covalent bonds. If it is excess, you will not score. If it is less, for example, if you write like this, you will not get. It must be this way, so that 1, 2, 3, 4, 1, 2, 3, 4. Place all the remaining residue into a boiling tube. Add distilled water. Shake thoroughly. So the residue is insoluble. The solid is insoluble in water. If it is insoluble, then it means it is non-polar. Anything that is not soluble in water, then it is non-polar. Non-polar. Divide the mixture into 2 portions. To the first portion, add the rest of the solid sodium hydrogen carbonate. Then divide the mixture into 2. So bubbles, effervescence occurs, viscing occurs. Now you see now in the mixture which is insoluble in water, effervescence is occurring. Now this one is the correct answer, or this one present. Effervescence occurs, it is hydrogen ions present. Why is this answer correct? We were told solid F. But if we were told that you are provided with organic solid F, then this one will not score. This one will get 0. The correct answer should be RCOH present. So what determines the correct answer here is the root of the question. Whether the question was saying you are provided with solid F or organic solid F. Any student who will write RCOH here will get nothing. It will be ignored. Instruction will be ignore. To the second portion, add 2 drops of bromine. Yellow color of bromine water persists. So if it is not changing from yellow to colorless, then it means the double bond, that is the alkenes and the alkynes, are absent. Are what? Absent. Thank you. Remember to share this video to as many people as possible. Usikue mchoyo. Kushare ni free. You just share to WhatsApp. Unafinya hiyo arrow iko hapo. Kuna kitu iko hapo hivi naenda hivi, the arrow hii, So unafinya hapo na una copy link unatuma kwa WhatsApp and even anywhere you want to send it to.